Hello, organic chemistry folks. Yes, another lecture. This one shouldn't be too bad. It's going to be over infrared. You should recognize a lot of this, so it shouldn't be too hard. But okay, let's go ahead and get started. So, once again, we'll go through our fundamentals, how it's supposed to work, the functional groups, how to interpret this, and some of its stranger uses. So the idea here is that molecules have various degrees of motion and that are all energy based. We all understand molecules can be translating through space, which means basically moving up, down, left, right, front, back. They can be rotating through space, as well as rotating along bonds. And also, there's going to be various bends and stretches, as well as things such as electronic excitations, where we get into the UV visible. But for the most part, we will focus on the stretches and bends. That any given molecule has a 3n number of total molecular movements, where n is the total number of atoms. So, like a single atom only has one movement it can do, only 3 movements. Up, down, left, right, front, back. The translation in the x direction, y direction, and z direction. A molecule with 2 can only have 6 spaces, 6 things it can do. And so on, 3 can have 9, so on. Well, for those given 3n movements, 3n minus 6 of those movements will be vibrations. So subtracting out those 6 are coming from the 3 types of translations and 3 types of rotations. So those 6 movements, everything else of those movements are vibrations. And for linear molecules, where one of their rotations doesn't accomplish anything, because if you're looking at it from the top and it's all straight up and down, rotating, spinning like a ballerina doesn't actually really change the molecule. So it's 3n minus 5. But so the rest of those movements are all vibrations. Now, each vibration is unique to every molecule. They have a specific molecular orbital above the ground state, requiring a low energy absorption to achieve this. So, if you look at if we talked about the molecular orbitals, there's actually small little movements up and down, like tiny little stair steps that are going to those vibrations. Besides the big jumps to excite this from, the d orbital to the s orbital. There's tiny little stair steps of vibrations. Now, the infrared spectroscopy will detect these absorptions and correlate these absorptions to a feature present within the molecule. Now, so of the whole electromagnetic spectrum, infrared radiation can be broken down into the near IR, which is our 2.5 to 0.8 micrometer range, mid IR, which is 25 to 2.5 micrometer, and the far IR, which is 250 to 25 micrometer. Now, most organic vibrations will occur within the mid IR range. Due to this very small range and wavelength, the data is often presented as wave numbers in reciprocal centimeters, where 1 centimeter is equal to 10,000 over 1 micrometer. So, this means our 25 to 2.5 micrometer is actually 400 to 4,000 reciprocal centimeters. So it's kind of like how we turn Celsius into Fahrenheit to get the more nuance out of the small changes. The reciprocal centimeters allows us to get more nuance out of this really small region. Now, the vibrational frequency depends on two specific molecule-dependent constants. The spring constant, K or kappa, which directly relates the strength of the bond. Stronger bonds, stronger spring constants. Basically, how much force does it take to move the molecules apart? A strong bond is going to have a stronger spring constant. It's going to be harder to move this. Now, the other thing is the reduced mass of the atoms vibrating. The reduced mass is calculated very interestingly, but it's the sum of the two masses divided by the product of the two masses. So, for example, if I'm looking at oxygen-hydrogen bond, it'd be the mass 16 plus 1 over 16 times 1. While the spring constant may be similar to OH as it is to CH, the reduced mass would be 12 plus 1 over 12 times 1. And here's where things like deuterium can really play a big part, because deuterium isn't going to really have a stronger bond than anything else than a hydrogen, but the reduced mass changes greatly, because suddenly you, instead of having, say, 16 plus 1 over 16 times 1, it's now 16 plus 2, which is 18 instead of 17, over 16 times 2, which would be divided by 32 instead of 16. So a rather big change. So they take the square root, and then it's also divided by a factor of 1 over 2 pi c, which is the speed of light. That will give us our frequencies. So that is how every single frequency is determined. This stretch occurs at this particular frequency based on the masses of the atoms involved and the spring constant between them. So largely speaking, the lower masses involved, the greater the wave number. So the greater where this stretches at. 16. So like that's why carbon and hydrogen and oxygen hydrogen and nitrogen hydrogen all occur further on the left, as opposed to, say, carbon oxygen bonds. They're further on the right. Triple bonds occur before double bonds because triple bonds are going to have a stronger spring constant. They're going to occur further on the left than on the right. So, because of this product on the bottom, that's what's going to be pushing it to the right or left, largely. But all that just predicts where the vibrations occur. Not necessarily will we see those vibrations. How do we detect those vibrations? So, that just says, 3n minus 6 is the number of possible vibrations that can happen. Now, in order to measure a vibration, we look at the relative intensity of the infrared light transmitted through the sample. So we look at the incident light. So we essentially shine light through a control, see how much gets absorbed, and then we shine our sample, see how much gets absorbed. The wave number of the light absorbed relates to the strength of the bonds and the masses, but the amount of light absorbs relates directly to something that is not, well, relates to essentially a change in molecular dipole brought about by this vibration. So you got to think about, would this stretch change the molecular dipole? The more it's changing the molecular dipole, the more it's going to, the greater the degree of absorption. So things like like particularly polar bonds, if it would change the dipole, say moving it to left or right, we're going to see a very big, deep absorption. We see a lot of those for things like OHs, C double bond O's, where we see very polar bonds and seeing very deep stretches. But here's one thing to keep in mind. Certain types of stretches, even if it's a polar bond, may result in a net non-change in dipole. Take, for example, the linear molecule carbon dioxide. Carbon dioxide is a non-polar molecule. Just because the C double bond O is directly opposite of another C double bond O. If the atoms stretch apart, the net effect is this CO bond and this CO bond are still equally far apart from the center carbon, so no net dipole changes. However, if we have what's called an asymmetric stretch, while this oxygen moves right and this oxygen moves right instead of right and left, one oxygen moves closer to the carbon, one oxygen moves farther away from the carbon. A dipole would end up shifting to the right. And so an asymmetric stretch would see a polar bond. Or, for example, if instead of being linear, it were to scissor, so it looks like a pair of scissors cutting in. In that case, the dipole would move down with the oxygens. Once again, we would see a vibration there, but we would not see the vibration that would be this symmetric stretch, where both oxygens move in opposite directions from each other. So if there's no shift in dipole, it is essentially IR invisible. So sometimes that's going to happen. So we may not always see every possible vibration. So just let that be known. No, things like OH, I said C double bond O, very strong absorptions. Yeah. We'll build inorganic chemistry that uses molecular symmetry, so we can actually predict what vibrations we will see and will not be IR active. We won't worry about that. The absence of stretch does not guarantee the absence of a functional group. One of the things that's often discussed is if you have a symmetric alkyne, the alkyne stretch will not be visible because the alkyne can only stretch symmetrically, and if it's symmetric on both sides of if it's identical on both sides of that triple bond, you're not going to see it. So, for example, if I had 2-butyne, where I had a methyl on both sides of that alkyne, it's going to be invisible. However, if I had 1-butyne, we have a terminal alkyne, we will see it because the H is different from the ethyl group. If I had 1-pentyne or 2-pentyne, or I'm not sure if 3-pentyne would be, no, like 3-pentyne is the same as 2-pentyne. So 1-pentyne and 2-pentyne would be IR active because a methyl group and an ethyl group are different. So they would have a change in dipole, even though it may not be much. And so I included some examples of some of these stretches that you might see. You'll see symmetrical, where they stretch in the same directions. Asymmetrical, where they stretch in different directions. So this smooshes in while that stretches out. Twisting and wagging, so they either go up or they go up and down. Rocking, where they both go in the same direction, versus scissoring, where they both go inwards and outwards. And so this is just the molecules vibrating as we hit it with this infrared. So the basic instrumentation, you don't need to know this super much, but it's going to be interesting. So we use a chromator, to isolate individual wavelengths of light and pass them through the sample one at a time. The thermal radiation transmitted would warm a pyroelectric detector and thus generate a signal. The sample could be analyzed a variety of different methods, so depending on what type of instrument we have, depends on how we make how we analyze the sample. There's things like we used to use sodium chloride glass cells. So basically a salt glass cell, and would mix that on there. We might mix it into KBr and smoosh it into a pellet and analyze it as a pellet. We might disperse it in a type of mineral oil paste and onto a glass cell. The idea is that these things, this NuGel or sodium chloride and KBr, do absorb infrared, but they don't absorb infrared in the mid-IR region. Well, the NuGel does absorb some, but it's cheap and easy, so it's like if you have a really cheap instrument, yeah, great. But sodium chloride and KBr absorb maybe in the far IR, so if it's outside the window of what you're looking at, it doesn't really matter. So, early monochromator prisms were either made out of sodium chloride, KBr, or cesium iodide, because these guys won't absorb the right wavelength. But so what we have is the attenuated total reflection Fourier transform IR. So ATR allows the analysis of a neat solid, or a thin film that we're going to deposit after the solvent is allowed to evaporate. So we're going to use a crystal with a high degree of refraction, so either germanium crystal or zinc selenide crystal. So we're going to deposit this onto the crystal. We're going to pass the IR beam through the sample, and it's going to bounce back and forth, transmitting absorbing each time as it goes through, and then bouncing back in to the detector. So either way, we're either having multiple bounces into the sample, or even just one bounce into the sample, but the light is basically refracted from the crystal into the sample, and this way we're avoiding we have to have some sort of solid that will absorb IR. It avoids the NuGel paste, usually gets a much better detection. Now, what a Fourier transform is a mathematical method of analyzing a lot of information quickly. So if you were to, say, try to do it normally, you would have to, as I said, cycle through every single absorption wavelength, one at a time. Check this, 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 and analyze each one. What a Fourier transform is it essentially creates a beam splitter and a moving mirror. You create a full spectrum of IR light, and you create a series of constructive and destructive interference so that certain wavelengths are intensified and certain wavelengths are blocked. So the instrument scans essentially multiple wavelengths at once. Wavelengths become duplicated, and a mathematical equation is applied to essentially turn this back. So if I test wavelength 1, 5, and 18, and then I check 2, 25, and 32, and then eventually go through all of them several times with multiple different combinations, the mathematical function will figure out what was the real absorption and what was the fake absorption, and what was a null peak. And so it can scan a lot faster and give a higher signal to noise ratio than just doing a monochromatometer and diffraction gradients. In general, if you're using a Fourier transform, you can get a signal to noise ratio of the square root of the number of scans. It will be your signal to noise ratio. So you're looking at how much peak you have versus how much background, how much of the flat surface you have. The more scans you do, the lower the baseline is going to be, because The problem with a monochromatometer is if you're scanning through all the things, say, just one time, if there's any stray cosmic rays or anything else that outside of your outside of the realm of you protecting it, that you can't really help, some instrumental error or something else, and it hits it during one particular scan, you're going to get a very high peak for that scan. And you won't be able to control it, you won't be able to know it unless you scan this multiple times, which takes way too long. This way, if you have, say, cosmic ray that hits during one scan, it's going to be averaged out as it looks at that guy multiple times through a whole series of different tests. So it helps stop instrumental error, essentially. Now, how do we use the IR? You should already know this, but how do we use the IR? The IR is going to work best as a supplemental tool in conjunction with other techniques. In a perfect world, you should have an IR and an NMR. But the IR is going to tell us a bunch of functional groups because stretches in the NMR, you can't always tell what the functional groups will be attached to, just that they are there. The IR will be there to help us know, oh, there's an OH stretch. Oh, there's an NH stretch. Oh, there's a C double bond O. Will help tell us what functional groups are present. IR can only be a positive confirmation of a functional group, not a negative. We can't discount something being there just because there's no peak. So we're going to look at it through a series of peak ranges for several common functional groups that can be present. Now, depending on your source, these IR ranges can vary a bit. There are far more known functional group peaks than we will bother to mention, but we won't cover them as they are not always going to be there. So, first range is 4,000 to 3,200, which is our OH and NH range. These peaks tend to be very broad and intense, with OH being a much stronger peak due to greater electronegativity. The broadness of the peak comes from hydrogen bonding. So as long as the sample is concentrated, or in water, or something or have like some other oxygens in the molecule, you should see hydrogen bonding. But if the sample is sufficiently dilute, or you measure it, for example, in the gas phase, these peaks will not be broad. They will become very sharp because no hydrogen bonding. The N could have a primary NH, which would be NH2, should have two broad peaks. But a secondary NH will only present as one peak. So if you see two sharp-ish but broadish peaks, you might have a primary N as opposed to a secondary N. Now, if these guys are adjacent to a carbonyl, so like a carboxylic acid or amide, they will shift to a lower wavelength. So, for example, we'll shift further to the right. But in general, OH is 3,300 to 2,500. Oh, that'd be with the amide. And NH would shift from 3,350 to 3,060. So they're shifting to the right a little bit. Now we have our CH bonds. These guys are going to be great in quantity as long as there's a lot of CHs. And the peak range will depend on the hybridization. Largely, we'll see a lot of sp3 hybridized carbons, which will be in the 3,000 to 2,840 range. Most of those can be safely discounted. However, going above 3,000, that's when you get into the alkene alkyne. So a sp2 hybridized CH would be between 3,100 and 3,000. And a sp, so alkynyl CH, would be about from 3,300 to like about 3,200. So those would be a good way to say this would be only present in a terminal alkyne. This would be present in most alkenes, but doesn't have to be present if it's a quad substituted alkene. Now, an aldehyde, which would be a terminal carbonyl, shifts below the CH3, because 2830 to 2695, having to do with pulling electron density out of the CH bond, making that bond a little bit weaker. So it's shifting further to the right. Our triple bonds, so jumping back real quick. So 2695, so about 2700. Now we have a big gap. So 2300 to 2100. We have our nitriles, or alkyne C triple bond C. Nitriles will tend to be very intense because you're going to see a very sharp change in dipole moment because of the CN. These will tend to be weak to moderate intensity because most alkynes, it's C bond, not very strong. But as I said, if this is symmetrical around the alkyne, they won't be IR active. And if you have any CO2 impurity, it would appear in this region as well. Then from there, after 2100, you have a big gap to the 1850 to 1500, where we have our double bonds. Our carbonyl peaks would be 1850 to 1550. This large range, why it's not very why it's so wide, has to do with a lot of inductive effects, hydrogen bonding, resonance, ring strain. All these things can have an effect on basically the spring constant. So it's going to push it one way or the other. But these tend to be very intense. Alkenes tend to be very moderate, from 1660 to 1600. But once again, they can be affected by resonance and ring strain. And aromatic peaks can show up between 1600 to 1550. Now, we won't really worry about these too much, but amines, so C double bond N, can show up in here as well, 1700 to 1600. And a strong NO stretch from a nitro group can show up in this region at 1550 to 1500. So when you're looking at nitrobenzenes and whatnot, you should see some of those in here. Now, from there, we have the fingerprint region. Generally speaking, it's such a large mess, we don't try to use most of this region. This would be all the bends and stretches, a lot of which that overlap with each other, so there's not a really sharp spot, so we don't worry about it too much. However, if you see a very strong peak between 1300 and 1000, it could be the presence of a CO stretch. So that alcoholic stretch or ether stretch could be appearing in there. And the moderate to weak one from 1350 to 1000 could be a CN stretch. But trying to guarantee that is what you see is not always the most useful. So don't worry too much about that. And finally, if you care to look there, just outside of the fingerprint region, just below it, right at the cutoff, is some aromatic CH stretches. These are not always the most reliable. NMR would be a better use. But so things like monosubstituted benzenes would have a strong band in these two spots. Ortho-substituted, which we'll learn about later, was a 1,2 substituted benzene, a 1,3 substituted benzene, a 1,4 substituted benzene, and various tri-substituted benzenes. But all of these are just some things to look for. So, now, as I said, we don't have to worry about most of these, but if you had boron would show up here. Silicon would show up in here. Halogens, CF, that's going to be in the fingerprint region. CCl is going to be in that aromatic region. CBr is also going to be in the aromatic region. CI is going to be in that aromatic region, just at the very bottom of our mid-IR. phosphorus bonds going to be way over there, and phosphate. So, like the phosphoric acid stuff is going to be 2700, 2600. Things like thiocyanide going to be in this region. Now, so looking at this, to look at this and see this might be able to give you some help. Now, these peaks are not always the best because you have to then, these are not labeled. So we have to look, there's 33,000, 29, 28, 25, 29, 28, sorry, 27. So notice that this peak is unusually low. And we have right here 19, 18, 17. So there's something like 1850, a strong double bond, 1850 carbonyl. And what this looks like is this is not an sp3 hybridized CH. This is an aldehydic CH. And so this is an aldehyde. Now this one still has a 19, 18, just about 17. But there's no peaks lower than 2800. So this is a ketone. We have the carbonyls in both cases. However, this aldehydic peak helps tell us that this is a terminal carbonyl as opposed to an internal carbonyl. Can we tell? They both have the formula of C6H12O. So this tells us there's one unsaturation index, probably not a ring. Looking at this, C4H8O versus C4H9, or HN, H9O. You can see right here, very broad peak. That is an OH. And maybe this is a ring, maybe it's not. But in this guy, see, it's still very broad, but you see two little humps right there in that region. Two very distinct humps. So that might very well be a NH2. Just want to show the difference of that. They're very broad, still very broad, but it has some humps in there that shows that there's two peaks associated with that. And both these guys are C4H6. So what do we have here? C4H6. So the unsaturation index is 2 degrees of unsaturation. 2 degrees of unsaturation. What we have here, there's our sp3 hybridized. In this region, 2000, 2100, we have a very sharp, very small alkynyl stretch. What we have here, 31, 32, there's 33, so this guy is a CHSP1 hybridized stretch. It's a very sharp peak from a hybridized CH stretch. So there's the alkyne, and there is the alkynyl CH. This is a terminal alkyne. This is our 1-butyne. Now this guy doesn't have a whole lot of anything. We have the CHSP3. We do not have an alkynyl stretch. We do not have a CH alkynyl stretch. What this guy is an internal alkyne. It's the 2-butyne I told you about. We'll see it doesn't have the C triple bond C stretch because of the symmetry. And it doesn't have a CHSP1 because it's all methyl attached to the CH triple bond. So this is kind of how we can use this. We're going to use this in addition to our NMR to go, oh, okay, there's an alkyne. Oh, there's a nitrile. Oh, you typically have a molecular formula. You can typically be able to find an unsaturation index. And we'll use this to try to find key functional groups that we're going to build off of. So that is how we can use the NMR. that is how we can use the IR. And then hopefully this will be a review.